Able to do it? Well, page 22, right? So the first one, degree of 1, so that's linear. So all you would have to do if it's a sketch, degree of 1, y-intercept of 5, negative leading coefficient. So we just make sure we go 0, 5 on that. And it's linear, so it's just going to go like this. That's it. You would get a mark there. The next one, constant, y-intercept of negative 2. A constant is just a horizontal line. Okay. So you would just stress that it's going to negative 2. And it's just a horizontal line like that. Next is degree of 3, 3 x-intercepts, positive leading coefficient. So we go C. It definitely has to have 2 turning points for that to happen. So we go positive leading coefficient, so it's going to do something like this. We got 1, 2, 3 x-intercepts. They're not telling us what specifically, where specifically, just that there are 3. Degree of 2. Range is greater than or equal to negative 4. So that tells me, if it's greater than, it tells me that it's pointing up. So my vertex is going to be somewhere in the negative 4s. So it doesn't matter how you, just make sure that this is something. So this would be 2, negative 4, let's say. That point right there, the vertex is at negative 4. You could make it go right, the vertex be right on the y-axis, which would make the vertex your y-intercept as well. It doesn't matter. It would all fly. Okay. Is there anything else? No, that's it. So it's just checking for understanding. Okay. So there we go. Let's move on. Let's go back to page 45, 46. 45, 46. So we talked about creating or generating our own table in order to perform a regression. And quadratic is the most common one. Okay, quadratic is the most common one, but linear and cubic is not to be overlooked. Okay, types 1 to 3 require you to create a table when it comes to quadratic. What is 1 to 3? So if you go to page 45, I call type 1 the profit / revenue. That's what we covered yesterday. Okay. Wait, what happened there? Revenue. Type 2 is the fencing. We've done these in grade 11. Okay. Fencing type question. Type 3 is the story, right? Story, find third point, basically. That is going to be the key here. Type 3 is find the third point given the story, given the context. Okay. So these are, you know what, no textbook will ever say that there are 3 types. They'll just throw things at you. But if you can kind of just make these compartments, it kind of helps to position them in a certain category. So this, I would add this to page 45 to help you out. And I'm going to finish 46 because I didn't finish that page, but I won't do the graph in this case. Just E there on page 46. If you come with me to 46, at the very bottom there, we never answered what ticket prices would give you that profit. line. Here it is. If you want a profit of 450, right, this is on page 46, you let y2 equal to 450, and then you find those instances where that would be the case. Okay. So essentially, if this is your graph on your calculator, this is your 450 line. You will have a ticket price on the lower end that gives you that profit. And you will also have a ticket price on the higher end that will give you the same profit. And the reasoning is that if you sell it at cheaper, you're going to sell more of it than if you sell it at a higher price. You may sell fewer, but still achieving the same profit. And if you're in business, you understand that, right? So here we have, this one is 0.49 cents, if you find the intersection there. And this one is 2.31, $2.31. Okay. Let me just check. Yeah, okay. So explain why there are two possible prices. Okay, I'll do that here. A lower price will result in more sales, while a higher price results in fewer sales. Both end up giving the same profit. You could figure out how many tickets are sold under 49 cents per ticket and how many are sold at 2.31. But we're not going to do that. I think you get the picture here. And I will make sure in our notes we omit 47. I think what I will do is I'll scan these pages. So what I omitted, if you still want to look at it, if you're bored, right, you look at it and you make sense of that. Okay, so let's go to 47. I'll just say, you try. If you want to try that one, I will post this page. And we're gonna skip fencing, not because I don't care about it, it's just that it's not as popular. I haven't seen a whole lot of that. So we're first gonna do the story, and then we're gonna come back to fencing. Okay. Let's go to story. So we're going to 52. Page 52, type 3. You are provided with 2 points. You find the third point using symmetry. That's where it's at. Okay, that's what this is all about. And I'm also going to skip this whole slide because we've done this in grade 11. I'm just going to jump straight to the example. Okay? So I will just say, see examples. So you don't think you fell asleep during my lesson and you didn't copy this down or something like that. I'm always ambitious when I make these booklets, but I don't end up using every single slide. So let's go to 53. That's where our first example, and I'm going to make sure you understand at the top, type 3 story, right? Write it nice and big on page 53 so when you flip through this booklet, you see it. Stands out. All right, so let's get started here. Roger would like to recycle his beverage container. He throws his container up from a height of 1.75 meters. Estimates that it reaches a maximum height of 2.8 meters after 0.75 seconds. What would we call this point right there? Vertex, right? And you can guess that this is going to be a parabola because it's something being thrown, right? It has that parabola path. The container lands on the rim of the recycling bin. I'm going to use a different color for that one. What does that statement tell me? Does this ever hit the ground? That's what that means. So you pick up on those little things that they throw at you, right? The bin is 0.65 meters tall. That's also worth mentioning. So very short question, but lots of information everywhere. Here, you don't even have to guess. It just says, determine the quadratic equation that models the path of the container. I would strongly suggest you make a sketch with these ones, with the story. So and I do not care if the scale is proper. I don't care. It's just for you as a reference. So this would be your time, and this is your height here. And let's see what happens. So the container is thrown from a height of 1.75. So somewhere, let's say it's somewhere in there. But we know that this is point number 1. That's point number 1. So we're going to go 0, 1.75. Okay. It's thrown up, right? Reaches the maximum height, which we're going to label in a bit. Then comes back down and it lands on the rim, right? And I know the rim is a little lower than when it started because it's 0.65. Does that make sense? Zoom into that graph, Mr. Dirksen. Sure. Let's try that again. Right? We start here, we reach a maximum height, then it lands here. Okay. We know that the vertex is 0.75 seconds and then 2.8. Make sure you don't mix these up. Okay, time first, that's your x variable, and then the height next. So we go 0.75, 2.8. Boom, that's our point. Second point. The third point, I found this question interesting because we know that it lands on the rim. We don't know what time, but we do know that it's 0.65. So I wanted you to think that that's perhaps my third point, but it is not. How could we find our third point? You look where you started. You started here. You look right across. You look right across the parabola, and it is there. That's your third point. Okay, that's where we're gonna find our third point, and it's going to be. We know that if we look right across, we're gonna come back to a height of 1.75. And this is where you use symmetry. If it took you, let's cut this, it's not quite in half, I apologize for that, but if it took you 0.75 seconds to get to the highest point, it will take you another 0.75 to get back to that same height from where you started. So in this case, I take that and I just multiply that by 2, which gives me 1.5. This is the third point. That is my third point. And you need 3 minimum for a parabola to for you to be able to do the regression. So this is what I like to do. Time and height. Have like a little table. And so you put them in 0, 1.75. That's where you started. Then it's 0.75, 2.8. Then it's 1.5 back to 1.75. So this is a very classic, right? You start at a height, initial height, you come back to that height. And it takes you, right, the same amount of time to go from 0 to the middle, and then from the middle back to the same height than when you started. So now we say, well, this is going to be my L1. This is going to go into my L2. We go stat, calc, quadreg. Very important that you tell us which regression you're, oh, you can't see that. My bad. We're going to perform our regression here. Yes. Turn on plot 1. So I'm going to go stat, edit, clear, 0, 0.75, 1.5. And over there it's 1.75. It's very tricky, this one, because there's a lot of 7.5s and 5s, so you got to be extra careful here. And then I will perform the regression. So I'm going to go stat, calc, quadreg, second 1, comma, second 2, comma, alpha trace, y1 you go, hit enter, and there it is, negative 1.87 x squared. No e's, right? I learned my lesson, right? Plus 1.75, which makes sense. It also makes sense that it is a negative leading coefficient. And the reason I'm saying that is sometimes students make a mistake in their points and they get a positive. So your can would be going up, right? You're like somewhere on the moon or something, right? So you got to watch out for that. Just a quick check. All right. Let's graph this thing. I'm going to hit graph. Probably not going to work for me. Yeah, I see it, but it's not a good graph. You know what? I'm going to go zoom standard on this one. My y-intercept is just 1.75. Zoom standard is probably going to do the trick here. Right? Obviously, we just focus on this first quadrant here. I'm happy with this window. I'm just going to leave it. How long does it take for the beverage container to reach the rim of the recycling bin? Reach the rim of the recycling bin. Right. When does that happen? Well, time when it reaches the rim, which is at a height of 0.65. That's what's happening here. So we're given the y, so y2 is equal to 0.65 second trace 5 to get that. No, sorry, 0.65. There it is. And remember, you don't care about the negative instance here, you just want the positive. So from time 0 till it gets there. So second trace 5. I only care about that one over there. Enter, enter, enter. That's 1.82, 0.65. That's the intersection. So it takes 1.82 seconds. You're done. And so now I'm just asking you questions that I could have asked before, right? When you were just given the equation. So nothing really changes what happens after. Basically, my focus is on this part right here. You coming up with your equation. That's what we're focusing on. So I might go a little faster here. How long does a container remain below 2.5 meters. This is going to be a delta T situation. Probably. I don't know. Actually, I should look. I'm going to see here below 1. So I'm going to go y2 is equal to 2.5. Yeah, so there are two instances where it does. So you know what? I'm going to zoom in here, or at least change my window slightly. X min, I'm going to go -1. Y min, I'm going to go -1 because I don't really care about those. My X max, you know what? To be honest, if you have it at 5, you're going to be just fine. My Y max, the highest height I get to is 2.8 according to this scenario. So if you go to 5 there, you're fine. So it's just zooming in a bit more. So we want to find these two instances, but what is it asking us for? Time above it or below it? We want to find below it. So how do you do this? Well, I'm going to find these two instances. Let's just go ahead and do that. Second trace 5. I will make a sketch here for you. Okay, we just focus on this part. This is the 2.5 line. Second trace 5. I'll find the first one. This is the first one here is 0.3491. And the second instance, 1.1509. Sorry, I should probably make a line like this. That's that one. And this is that one. If I go delta T, if I go, right, 1.1509 minus 0.3491, what am I going to get here? Let me just calculate this first. That's 0.8018. Is this time above or below? Above. And if you're not sure, just ask yourself, between these 2 points, when you subtract them, when you find the difference, what's happening between these two? Well, you can clearly tell that the curve is above, correct? So this above 2.5 meters. That's what you found here. If you want time below, the fastest is total minus time above. That's how I'm going to approach this. My total flight time I already figured out, it's 1.82 seconds. I'm going to subtract 8018 from it, and that is going to be my answer. 1.018, so it's 0.2 seconds below 2.5 meters. This is the final answer. That's what I really wanted. Chances that this is going to be asked of you are not very high, but you're ready for it. Most of the time, it just involves you subtracting. So they would probably ask for time above in this case. Graph this scenario. I'm also going to say you try. Go ahead. You try. And I will post this. So if you want to practice graphing, you go for it. But you already know what's happening when it comes to the graph. You should know at least how to graph at this point. What's the domain and range? That is very important to know how to state that. Domain is your time. You start at time 0 and it stops when it lands on the rim, which we know is 1.82 seconds. My range, the lowest height you ever get to is the rim of the can, right? So that's 0.65. and the highest you ever go is your vertex, which is 2.8, or is found at the vertex, which has a height of 2.8. So it's always smallest then largest, okay? That's very important for you to understand. So this is your story. And here's the cubic one. So story, I'm just going to tell you this. Sometimes you don't underestimate the power of starting on the ground. Sometimes like students are like, well, what's the point? The point is if you start on the ground, it's going to be 0, 0, right? If you kick a ball from the ground, at time 0, you are at a height of 0. So don't underestimate 0, 0, because a lot of students are like, where's my first point? It's 0, 0. So if you see it, use it. It's very, very helpful. Let's take, I'm going to warn you as well, one more thing. Sometimes the question gives you this and this, but you're going to have to find the vertex, like what's the x value at the vertex. The answer is not multiplying by 2, but you're going to have to divide by 2 to get the middle point, right? The time at the middle. So watch out for that. I want to do the cubic one here on page 54. You need a minimum of 4 points. Other than this one, cubic regressions, like you making your own points, are also not very common. This one is the classic one, the volume question. So pay close attention to this one because you haven't seen this one before. So let's assume you have a rectangular sheet of cardboard measuring 40 centimeters by 15 centimeters. Okay. Using a cubic regression, determine the dimensions of the squares that should be removed to make a box with a maximum volume. I will also say this, assume that the top is open. Doesn't really matter because it's volume, right? But sometimes they throw that in there, and I just want to say, hey, let's throw that in there. Okay, so what do we know about this sheet? So imagine you have this sheet of cardboard, and you're going to cut off here, and you're going to fold the lips, right? You're going to fold these lips up to make your box, okay? So this is what? We know that this is 40, and we know that this is 15. And so what we're going to do here is these things that need to be cut out, they're going to essentially represent the height of the box. So if that makes sense to you, if it's the height, if you cut this, and if I fold this up like this little lip up, that's going to be the height of the box essentially. So we're going to say, let's call this x. The height of the box is x. So everywhere you go, all around this. So we're always assuming we're cutting out the same amount on each corner of this sheet of plywood. Okay. So here's where I want to change things up a little bit. My length, this length right here, like the length of the box that is resulting from here to here, would be 40 minus, you take off an x here, you take off another x here, correct? So minus 2 times x. That would give you the length of the box. Does that make sense? If you're cutting off, if you go chink, chink, right, then this chunk here is going to be 40, which is the entire sheet, minus 1x on either side. Which means that the width of the resulting box, once you fold it, it's not going to be 15, it's going to be 15 minus 2x. like that. So this is my, let's call this length. Length is going to be 40 minus 2x. The width is going to be 15 minus 2x. And what's the height going to be called? The height is x. Does that make sense? Maybe you have to just follow me a bit more, but that's what's going to happen. So I'm going to try my best here. If you fold that box and you make your box, right? Look at that. Look at that. Isn't that pretty? Right? This long side here, this long side of the box will be 40 minus 2x. The height of the box is what this cutout is, this cutout piece here. So that's just x. And the width, which is this lip right here, is going to be 15 minus x, because we're going to play around with the values. We're going to find that magic height, the magic amount to cut off on each corner to get the biggest possible volume. There's such a thing. We can play around with it and find, like, what should this cutout be? Should it be this big? Or should it be this big? Or should it be, right? Like, we're going to figure that out to get the most volume inside this resulting box, okay? All right. Before we start, what is the greatest value that x can possibly have in this scenario? And I would say this, look at the shortest side. Between these two sides, this is the shortest side, correct? Let's go focus over on this side. If x is 5, right, you take off 5 on each end. 2 times 5, right, 15 minus 2 times 5, that'd be 15 minus 10. You would still have 5 left over on this side. But what's the maximum we can take off on either side? It would be 7.5, right? Because if this is 7.5, like if this x here is 7.5, and this is 7.5 as well, that would give you a width of 0, which would not be a box anymore, okay? So one thing you need to state, I'm going to focus on this one, right? That x has to be between 0 and 7.5. Think about that for a minute. Because if x is 7.5 exactly, right, then it's basically 15 minus 15, that's 0. That's not a box anymore. So we actually don't say equal to, it's just it has to be less than 7.5, but it can be greater than 0. It has to be greater than 0, obviously. So this is something, it's going to come in handy later on when we look at the graph, okay? So, what did it ask again? Determine the dimensions of the squares that should be removed to make the box with the maximum volume. So, we're first going to come up with our equation. And so we're going to start with this. Height, length, width. It doesn't really matter in which order you put them in. But the height, we can come up with just random values. And I'm going to use the values that I came up with in my key. This is the independent variable. This is the one that I just make stuff up. I just use numbers that I choose. So 2, 4, 6, 8. That's what I've used. If you pick numbers that are too big, you're going to get some negative volumes, and that's okay. But you just got to make sure you keep the negatives in place, because this is going to be a cubic curve, okay? So just keep that in mind. So if the height is, if x is 2, then what's the length going to be? I already know that length is 40 minus 2x. Where does the 40 come from? The fact that this sheet is 40 long, right? So this would be 40 minus 2 times 2, that's 36. Then I go 40 minus 2 times 4, that's 32. Then I go 40 minus 2 times 6, that is 28. 40 minus 2 times 8, which is 24. So I'm using the length that I've written in terms of x, which remember is the height ultimately of this box. Now, using the x values here, the heights, I'm going to also figure out the dimensions of the width. The width is 15, that's the whole sheet of cardboard, minus 2 heights that are going to be removed. So this will be 15 minus 2 times 2, that's 11. Then it's going to be 15 minus 2 times 4, which is, that's 8, right? So 15 minus 8 is 7. 15 minus 2 times 6, that is 12, right? So 15 minus 12 is 3. And here we have a bit of a problem, but not really. 15 minus 16, that's negative 1. What? Remember, we surpassed, what is the maximum height that we can technically choose that this is valid for? It's 7.5. We have surpassed it. So this is where the problem lies when it comes to the domain and range. But just follow me here. We're going to figure this out. What's the volume? Volume is length times width times height. So we're just going to go 2 times 36 times 11 to come up with this one. 2 times 36 times 11. Then it's 4 times 32 times 7. Then it's 6 times 28 times 3. And it's 8 times 24 times negative 1. What? We're going to have a negative volume? That's weird. Remember, we're making the regression of the curve, and the calculator doesn't really care right now whether the volume, because it doesn't even know that the volume is what our y value is. So we're just going to go ahead and calculate that. You know what? I'm just going to give you the numbers. This is 792. This is 896. This is 504. This is negative 192. Right? Piece of paper. Right? You determine what the square is that you're going to cut out. Right? You cut out that square. And this has to be the same as the one over here. Okay? You would cut it out like that. Has to be the same as you would cut out on this corner. So all the squares that you cut out have to be the same. So this is x by x, right? And so based on what you decide to cut out, and we've made some decisions here. We've picked some random, hey, I wonder if I cut out a 2 by 2, what would that give me in terms of my volume? Because remember, it will affect the length of your board. It will also affect the width of your board, right? Depending on what the square is that you're cutting out. So that's what's happening here. Can you have a negative 192 box? A volume with negative? No, you can't. But the calculator will take care of that. So let's come up with our equation here. So yes, the height or your x, your cut out, right? That's going to get our L1. That's one of the dimensions. We skip everything else and we put volume into our L2. L1, L2. Mr. Jackson, could I have put length into L1? Yeah, then you would come up with an equation that relates the length and the volume. But we're now relating the height and the volume. So we're going to go stat cubic reg, stat calc, sorry. Stat calc. cubic reg, and let's come up with, how would you know this is a cubic if I didn't tell you? What's volume stated in always? Centimeters cubed, correct? So that tells us, even if I didn't tell you, has to be a cubic regression. Okay. So let's do that. You should follow this one because it's a cubic. You haven't done cubic regressions like this before. So 2, 4, 6, 8, and then 792, 896, 504, negative 192, and then we go stat, calc, cubic regression. We could probably look at our scatter plot and first look at that, but we don't need to because we know where this is going. Alpha trace, enter. There it is. So y is equal to 4x cubed minus 110x squared plus 600x, and then there's 0 after that. So let's hit graph. Probably not going to work very well, but let's give it a try. Yeah. Bunch of stuff from the previous question. I'm going to clear y2. I'm going to turn on plot 1. I'm going to try zoom stat, to be honest. Zoom stat, let's see here. Hey, that's not bad. Not bad, right? We know this is happening. It's a positive leading coefficient, so I'm expecting it to go up at some point. I'm going to change my window a little bit. X min, I'm going to go -2. X max, let's increase that to, I'm going to go 20, 25. Y min, do I need to know the negative? Not really, not much, but I'm going to leave it there because I just want you to see it. X max, let's leave it there. Let's see here. If I try this, there's your cubic regression. I'm actually going to decrease my Y min a bit yet. I'm going to go -1,000 maybe. Oh, still not. -2,000. Still not. What do you want? How much money do you want? There we go. It's like my accountant. So this is the entire curve, but I'm here to tell you that it stops right there. The model for volume stops right there. We don't care anything past it anymore. And this is the reason. Let's find that x-intercept. y2 is equal to 0. Hit graph. You see that negative volume that is here? And the calculator used it to still come up with your model, but it wouldn't apply normally. I'm going to find that intersection. What is it? 7.5? You see that? And what did I tell you earlier? That we're kind of bound between 0 and 7.5. So this is where the action happens. Anything past it, you would get a negative volume. And then you get back here one more time and you hit this x-intercept. This is, I'm just going to show you that x-intercept, second trace 5. What do you think it's going to be? Enter, enter, enter. It's 20. Why is it 20? Because if you looked at this side right here, 40 minus 2 times 20, that would be your 0. So there's a restriction on the length as well. It can be between 0 and 20, but we don't care about it because this is our problem that occurs first, right? So we're just stopping at 7.5. We stop at the first x-intercept right here, okay? So, yeah, I know it's a lot of fun. Not. Right? So we're going to graph this anyways. So what do we need for it? We need our y-intercept. We already know what that is. That's 0, 0. That's also the origin. And that's also an x-intercept. That's both. So y-intercept and the x-intercept at the same time. And we know that the other one, the other x-intercept is 7.50. We've already determined that. We just need to find the max. So the vertex, second trace max. There it is. At 3.33, we have a maximum volume of this. I will make a statement here. Maximum volume is 925.93 centimeters cubed. What's the height going to be? Height of box? 3.33 centimeters. How do you know, Mr. Erickson? Right here. So if you have a square that measures 3.33, 3.33, if that's what you cut out of that piece of paper that I don't know where I left it, right? If this measured 3.33 on either side, you cut that out, and then you fold this, right, to make your box all around. Can't even fold paper, Mr. Erickson, you should be teaching. That would be the biggest box you can possibly make. I know I didn't cut it all out, but right there's your height, and not a very pretty box, but I hope you get the picture there. Do we want to graph it? Absolutely, we're going to do that quickly here. This is my height in centimeters. This is going to be my volume in centimeters cubed. What's going to work out here for us? We need to go all the way to 1,000 here. So if this is 0, we're going to go 500, 1,000, and here we're going to go, how about we go 2.5 at a time? I think that's going to work out great for us. Oh, sorry. Thank you. I'm going to go 2.5 on that one. 10. And here we go, 0, 0. At 3.33, I am at almost 1,000, not quite. $600, $700, $800, $925 is right about there. And then I'm at 7.5 right here. So we're going to go. I will show you that we omit this. Omit, okay? We're outside the domain, and at that point, we no longer care about it. And so you're like, couldn't you have used a parabola? That looks like a parabola. To be honest, yes, but the best model is a cubic. Okay, we always want the best. Okay, we're almost done here. So for domain, I will check with, I'm actually not 100% sure here. This is where I need to double check. I'm for now going to go domain, which is our length. We go from 0 to 7.5. And for range, we go from 0 all the way to 925.93. That's the highest volume we can have. What I'm not sure about is if this should be round brackets or square brackets. Because technically, if you had a 0 height, you would no longer have a box. I will check with Miss Yosik and see what she says. So hold on. I want you to practice. So just before you pack, just stay with me here. I'm going to say 64. I'm keying this one right as we speak. 64 to 68. So go to page 64. Or, you know what? You might want to write it down right where we ended up. It's up to you. I will do that again. 64 to 68. These are linear, quadratic, and cubic. Linear, quadratic, and cubic. Okay. And I really want you to try them. If you're stuck, I will hopefully help you out tomorrow.